Good day, statisticians. In our last video, we were just learning about power models as contrasted with exponential models as really the two methods we'll have of dealing with nonlinear relationships between data in AP Stat at least, right? And we saw that both of them were generated by doing some type of logarithmic transformation, right? For an exponential, you took your x values and you left them the same, but you took all your y values and you straightened it out by taking the natural log of the y's and plotting that relationship there and finding out that it comes out to be straight. And the power model, we'll get a similar kind of equation, but now we're going to take the natural log of x and the natural log of y, find a linear equation using least squares regression for natural log of x versus natural log of y, and then use that to make predictions. Now, the whole point was there is that in a power model, this guy should come out to be straight. So I want to show in class today so a couple of things. I'm going to show that, in fact, if this is the model, that this would be straightened by doing natural log of x, natural log of y, right? But I also want to demonstrate that basically how the equation, once we get it, using the least squares regression, actually will generate what we want it to in terms of a model that looks in the correct form. And so in our last video, we had actually generated this equation right here. Remember when we were looking at the relationship between the lengths and the diameters of the humerus bones of African antelopes. How exciting, right? Fun stuff, right? And we got this equation and we said that this was a power model, but we also said in general that a power model is supposed to look something like this. So it's supposed to be something like y hat equals a times x raised to the b power. This doesn't look anything like that. So I want to do a couple of things. First, I want to show that the equation that we would get of this form is equivalent to this guy, and then I'll do some stuff that's a little bit more general. So here's the idea. Remember in our calculator that there are other types of regression. I showed you in the very first video on nonlinear models that you could use the exponential regression thing here. Actually, there is a power regression function too. So if I go to power regression, and remember I had all my data stored in L1 and L2, my original x's, my original y's. If I just did L1 and L2 like this, and I hit calculate, then actually the calculator will generate for me a power model, right? It will generate something for me of this form without me doing all these crazy transformations, right? So according to the calculator, the correct equation here would be y hat equals, let's write it out. That would be, what do we have here? 24.0964 about, right? Times x raised to the, let's see, what power do we have here? 0.65993 or so, right? So that is our power model equation, and that is in this form. Now, what I want to show you is that this equation here, aside from perhaps some minor rounding error, is exactly the same thing as this. So this was where we were making a prediction earlier. We don't really need this guy anymore. Oops, this was a different layer. Let me see if I can get back to that layer. Can I erase you? Yes, I don't need you anymore. Goodbye to you. You were beautiful, but now you are gone, and that's fine, right? All right, so let's show mathematically that this should come out to be the same thing. So let's start to undo all these natural logs and things like this, right? So one thing that I can do if I start simplifying this mathematically is I could simply do e raised to these powers. Do you agree? So I could do, if I want to get rid of natural logs, I could do, I could say I could do e raised to this power. So if I did, let me get that pen here. If I did e raised to this power and e raised to this power, since the e raised to a power, an exponential function, is 1-to-1 and strictly increasing, or strictly decreasing, but it's strictly increasing here, then we're good to go. So this would just become y hat. Now on this side, we'd have e raised to the 3.18206.3 power, plus 0.659927 natural log of x. Okay, now this simplifies some more because remember, whenever you have the sum of two things in the exponents, that means it really can become a product. So I can write this as e to the 3.182063 times e, because it's with the same base, 0.659927 natural log of x. Now, Same, another kind of principle we can apply here. Of course, this e to a bunch of stuff is just a number, right? So this guy is just going to chill. I'll just rewrite it. I got 3, and I'll eventually figure out what that number is in just a second. 2063. Right now, one of the things that we can see here is I could, once again, when you have the product of two numbers in an exponent, you could really write this as the product of this times the natural log of x. Then essentially what happens is that this is the same thing as raising a power to a power. So I could rewrite this as e to the 0.659927, right? And then raise that to the natural, actually, you know what? I want to do the opposite. Let's do, I want to do the opposite. I just realized I want to put the natural log of x here, and then I want to take this numerical part, I'm going to put it up here. There's a good reason for that. I just realized as I started writing this, I want to do the opposite. Now, why do I want to do this? What's e to the natural log of x? Well, e to the natural log of x, that's the same kind of thing that happens here. These are inverse functions, and so they will undo one another, for lack of a better term. And so this will end up just becoming, again, e to the 3.182063, and e to the natural log of x just is x. X to the 0.659927 power, right? Cool beans. So the only thing that I'm going to have to do is simplify what this e guy is over here. And so if I go to my calculator and I say, oh, calculator, please tell me what is e raised to the 3.18201, oh, excuse me, it's not a 1, I almost misread my hand, 6, 3. That is, my calculator says, oh, where'd my pen go? I dropped it. Here we go. Calculator says that this guy is the number 24.09641 or so. And then I've got times x, and then of course I'll rewrite what the number we had here, which was 0.659927, right? And so let's take a look. All right, this equation, of course, this now became y hat. How did this equation, let me use a different color. How did this equation compare to the one that the calculator generated? Well, let me zoom out. Let's take a look. The one the calculator generated was 24.0964, 24.0964. I wrote an extra 1 there because around it's just how many decimal places I showed. And notice we had 0.65993, 0.659927. I just happened to show more decimal places, but these were exactly the same equations. Yes, these are exactly the same equations. And so the good news is that the methods that we did are identical with the methods that the calculator does. Essentially, everything, the way we get these nonlinear models is by using this logarithmic transformation and then converting it back. The good news is for us in AP Stat, if we're showing our work, we're perfectly fine just by doing this. You don't have to do any of the algebra I just did here to show that it is an equation in this sort of power function this power equation form. You can just work with this guy. The bad news is, though, in AP Stat, we're not technically supposed to know that there is a power regression button down here. So, I mean, technically you could cheat and use it, but if you were trying to show your work on a free response question and know that the AP exam is entirely free response questions this year, if you referenced power regression in order to get your model, they're not going to give you credit for that because they expect you to use all these fancy methods by doing transformations, checking residual plots to see which model is the best fit, and then writing the equation in terms of logarithmic transformations with natural logs. You don't have to write it like this. They do expect you to be able to write it like this guy here. So that's just the way life is, okay? Statisticians. I just realized there was one more bit that I wanted to include in this video, so I stopped the recording, and now I'm starting again, and I'm going to add this to the end, because I wanted to show you in general the math that would prove, that this kind of transformation would straighten the power equation. So we had just shown that if we simplified this guy algebraically, we would get this power model, the same thing that the calculator would have generated for us just by doing power regression. But I wanted to show in general, and I had shown in another video that if you had an exponential function like y equals a times b to the x, and you did this transformation, you just took the natural log of y, it would end up straightening everything out. What I want to do now is to prove the same thing for the power, that if you had some function of the equation y equals a times x raised to the b power, if you ended up looking at the natural log of x versus the natural log of y, that would end up being a straight linear equation. All right, so that's what I want to kind of show. And this one's actually a super easy, simple algebraic demonstration here. So let me zoom in just a little bit. So let's say I had here, I'm going to zoom in just a little bit more. Let's say, again, I'm going to start with this assumption. Let's say we had the two variables that had the relationship y hat equals a times x raised to the b power, right? And let me make that red. Let me make that red. All right, so how can I show that this transformation will end up becoming straight? Well, let's just start by taking the natural log of both sides, right? We'll take the natural log of y hat. We've got the natural log of y hat equals the natural log of a times x raised to the b. Okay, let me put that in parentheses so you can see that. Okay, so that's nice. Now, what happens? Well, let's simplify the right-hand side here. I already have the natural log of y hat. If I had the natural log of the product of two things, then you should remember by laws of logs, that would be the same thing as the natural log of a, right? But then plus the natural log of the other product that I have here, which we forgot the end, natural log of my other term, x to the b power. Right? That's perfectly fine, right? Remember that the product of two things here can be broken down into the sum of two separate logs, and that's kind of nice. So let's simplify further, right? Now, notice that the natural log of x to the b, by applying the third law of logs, I can take this b and it can come hang out and move out to the front, right? So I could rewrite this as the natural log of a plus the natural log of just x here, but now out front I can put that b. Let me make some space for myself here. There's plus, and I could put the b right there. And so let's take a look. So here I had, again, the natural log of y hat equals the natural log of a plus b natural log of x. Well, let's think about this. This, my friends, is a linear equation, right? Recall that the natural log of a number is just a number, right? And so, I don't know, I could arbitrarily call the natural log of a something like, I don't know, some letter. Let's call it u, right? And then b, well, that's just a number. I could call it just, I've already got it there as b. I could just write it as b. And so notice that I have the natural log of x right here. And I'll write it all as red, natural log of x. And over here I have the natural log of y hat. Notice that this is just like a good old linear equation. Remember in Algebra 1 when you wrote down linear equations like y equals mx plus b, or like b plus mx? Well, we have the exact same form of an equation here. We have, except instead of having just y, we have natural log of y being in a relationship with the natural log of x, right? Both of these are in a linear relationship with each other because I took the natural log of x, I multiplied it by some number that acts like the slope, and I added some number to it. In this case, that was this natural log of a. And so this is a linear equation, a linear relationship between the natural log of x and the natural log of y hat. And hence why we should get straight data when we perform this transformation if this is the true relationship between our variables. Isn't that pretty neat? Okay, I'm sorry. I'm glad that I was able to finish off this video the way I wanted. Have a beautiful day and catch you on the flip side.